Good morning, and welcome to my session on Inside GPT, the maths behind the magic. I'm from England, so it's maths and Lego, rather than the other way around. I will be working through some Jupyter notebooks to show the demos, and there is a zip file. If you do want to download those Jupyter notebooks and play around with them, they do include the source code for GPT-2. So you can run GPT-2, you can put breakpoints in, you can step in and see how the models work. If you'd like to do that, I'll show that link at the end as well, if you do want to take a photo of it. So what I'm going to be doing, this session really follows on very nicely from Jodie's session and Michelle's session. And what I'm going to do is to look deeper into these language models, look at how the maths works. So we've heard in the last session, if you're present, about the concept of text comes in, it gets tokenized, we do embedding on those, we then add on the positional embeddings, and then we can use the attention formula to calculate and make predictions. I'm going to be looking at how that works in quite a bit more depth. A bit about myself. My name is Alan Smith. I'm from England. I live in Stockholm, Sweden. I work for a company called Active Solution. I've been writing code for money since 1995, programming as a hobby since quite a bit before then. I've been involved with the developer community for the past 20 years. I've been teaching courses, speaking at conferences. I'm also, like Michelle, an Azure AI MVP. I'm in the Azure AI Foundry category. And that's just kind of a reward that Microsoft gives. It's not about being clever or passing exams. It's about sharing knowledge with the community, which is something that I really love to do. And that's ranged from organizing conferences, speaking at conferences. I've assisted at Coder Dojos and taught kids about AI. Very occasionally, I publish something on YouTube, so there's a link to my YouTube channel there. However, according to the Phi language model, I'm part of Microsoft's impressive lineup of personas designed for interactive digital experiences. Alan Smith features a British accent, which can give users an engaging and distinctive auditory experience. I've got these various personal types. I'm also integrated with Cortana and Skype, apparently. So, large language models, they can sometimes come up with kind of crazy responses. This is often commonly known as hallucination. So another demo of that, I'm going to go in, and I'm really relieved. I love using GPT 3.5 Turbo because it's quick and it's one of the early models, so it's good at showing the weaknesses. And Microsoft announced that this model was going to be retired on Monday. It's now going to be retired on Friday, so I can actually do this. What I asked it to do, I'll do it again actually, because it's non-deterministic, we're going to get different outputs. I'm asking it to tell it about Alan Smith, the Azure AI MVP. So here, it seems to be doing a slightly better job than the Phi model. It's saying, I'm recognized for my experiences for the contributions in the field of artificial intelligence, and it's just talking about Azure MVPs, and yeah, I've been active in helping developers and organizations implement AI solutions, participating in forums, creating educational content, speaking at conferences. So this is good. Do we trust this output? Is this something that we would say? That is complete fabrication. And to prove it, I can change the discipline to PowerPoint. So tell me about Alan Smith, the PowerPoint MVP. Yeah. So now I'm recognized as a PowerPoint MVP. I go around and I help people improve their presentations. There used to be PowerPoint MVPs there in the Office discipline. There was always a joke in the MVP community that you become a Notepad MVP, so see if I can be that. Yeah. I'm good at Notepad as well, apparently. So what it's doing is just basically just generating stuff, because all these models do is generate the next probable tokens in a sequence of tokens. And whatever I put in, it's going to, the next probable tokens telling about Alan Smith, the cheese MVP, is that I'm an expert in cheese. So sometimes these models are factually correct. If I clear this, clear the conversation history, and I say, tell me about Alan Smith, the footballer. So there, we've got information about Alan Smith, the footballer, who's played for Leeds United. He was born on October the 28th, 1980. If we go to Wikipedia and search for Alan Smith, here it's not going to find me. I'm not that famous. I've still got a few years to go, though. Yeah. Born on October 28th, 1980. So here, it is coming up with factual information. And you know, in the previous two sessions, there's been a lot of discussion, how do we know that it's coming up with factual information? And that's a lot of you know, the reliability and so on. What I'm kind of focusing on this session is why does it do this? Why is it making these various types of predictions? So as I mentioned, I've got some LinkedIn stuff, I've got some YouTube stuff. Best place to contact me for questions is LinkedIn. I've been doing some fun stuff with AI. I like to do fun stuff. I was getting GPT-4 to play StarCraft, coming up with strategies. So there's a series of webcasts on that. That's one of the kind of hobby projects I've got. Also, before I start, I'd really like to thank other YouTubers who've helped to expand my knowledge and the general knowledge in the community. Andrew Karpathy's been mentioned. I think I mentioned him about 10 times during my workshop the past couple of days. And his name was also mentioned by Jody as well. He's got some fantastic videos. The GPT-2 model I'm going to demo today, I was at NDC in Oslo. I have a 5-hour train trip back to Stockholm. He's done a 4-hour video coding GPT-2 from scratch. So I watched through that video, drank a bottle of wine, and the demo is the result of that train trip. Also, others like 3 Blue 1 Brown, fantastic animations explaining how these models work. Even Code Bullet, I learned a lot about generative AI from Code Bullet. You may be familiar with a few of these channels if you've been hanging out on YouTube. Yeah, so many of you may be developers. Data scientists tend to use long words. So instead of settings, they'll say hyperparameters. Things aren't random, they're stochastic, and they don't have ideas, they have hypotheses. If they guess, it's a minimum likelihood estimation. And when you're training stuff, there's an epoch, which developers just call a loop. So GPT scenarios, the most common request we get, because this is what people think all large language models do, is they answer questions. We ask it how to make cheese, and it comes up with a solution for cheese. But they're also very good at text generation. We built a project for a Swedish local authority to generate the introduction to reports. And I can't show the system prompt for that, but this is a very, very similar system prompt that generates movie introductions, you know, these inner world where. And I've given it some examples. I'm putting parameters into the prompt. We can use it for text generation. We can use it for fact validation. The same authority wanted to validate their reports to make sure that they complied with various guidelines. So there's lots of things that we can do with these language models. Classification as well. We can analyze sentiment, figure out what languages are the same. They do understand different languages. We can also build copilots. So if we basically ask a language model to give me a breakdown of the Nobel Prize winners in Europe, they're very good at generating code. So if they understand a SQL database, they can generate SQL code. They can then run that SQL code on a database, get back information, and give statistical information. I built this as a prototype for the Nobel Institute because they were saying that ChatGPT doesn't give good statistical answers about Nobel Prize winners. Can you build something better? So we built this little proof of concept that does just that. It does have this side effect because I wasn't concerned about security. I've actually added myself as the 2025 Nobel Prize laureate for artificial intelligence by asking the model to do that. You can also change the city where various Nobel Prize laureates were born in because it will also do updates to the database. So we've got to be careful with this technology. Problem-solving ability is questionable. I speak at conferences in Belgium quite frequently. This is the duty-free at Belgium. It's fantastic. These bottles of beer are the same size of bottles of wine. Some of them are the same strength as bottles of wine. So I want to know how many of them I can fit in my little 30-litre backpack before I get on the flight. So I asked a Copilot, and it started doing formulas that I've not seen since I was at school. The volume of the beer bottle, the volume of the backpack. And this seems to be pretty good at problem solving. It's calculating the space. It's got this hexagonal packing pattern with a 90.7% efficiency. And now it's calculating how many bottles it can fit on each layer. And it finally comes up with the answer as being 95 bottles of beer. Something is wrong. It's got good image generation capabilities. It can generate an image of what that would look like, and there's me on the plane. I love their version of economy class. There's no aisle on the aeroplane, there's just seats. And it still does that today. So, I mean, these models are fantastic at some things. They're really, really bad at other things. The worst thing you can do is to ask a language model to multiply two floating point numbers together. you're basically asking it to do one floating point calculation. In order to do that, it's going to do several trillion floating point calculations, and it's probably going to get the answer wrong. So they're good at languages, not good at other things. So what I'm focusing on is the model. I'm actually old enough to remember this being a single in the charts, and the computer there is based on a Commodore PET. We had about 12 Commodore PETs at my school. That was considered really, really advanced at the time. I think they had 32K of memory or 16K of memory, so you could write pretty sophisticated programs. So typically, when you're building a chatbot, your system architecture looks like this. You have the user, you build some JavaScript wizardry to create a website that is able to have the chat interface, and you build an API. The input goes into the API, you have some prompts, you maybe do filtering, monitoring, logging, and then you call out to your LLM, which is hosted by another company. So this is the large language model API. And you can, if you want to, do retrieval augmented generation from data sources. You can also connect it up to your business systems, and you can build agents and do function calling and MCP and all of that cool stuff. So what I'm focusing on here is what goes on if we drill into what happens in the large language model API. It looks like this. You send in your prompts and parameters. There's billing, content filtering, monitoring, and logging. We then go into a process known as tokenization. And that will do the encoding of the prompts and the system prompts and the conversation that gets encoded to a stream of integers. That goes into the model. The model will use code and model weights. The code for GPT-2 you can get down to about 95 lines of Python. The model weights for GPT-2 is 126 million floating point numbers. So there tends to be a bit of code and tons of model weights. Now the model will predict the logits. We say that these models are non-deterministic. They will produce different outputs with the same input. However, this model itself, if we give it a sequence of input tokens, it will always come out with the same token probability in the logits. And we'll see how this process works, but what gives it the non-deterministic nature is a sampling process, and that's where we use things like temperature and top P to influence, out of those predictions that the model has made, which token are we going to actually use. So the stochasticity or the randomness comes from this sampling process. And these models produce tokens one at a time. So we've got to do this lots and lots of times to generate a large output. You know, generating an output of 100 tokens or 1,000 tokens, we've got to loop through and do that lots and lots of times. Then that goes through the decoding, we get back the text, we then do the billing, content filtering, monitoring, and logging to check that the output isn't generating anything inappropriate, and we send the response and the stats back to the user. So, to summarize, given a sequence of tokens, the large language model will predict the probabilities of each token being the next in the sequence. So we set in the cat sat on the, and the model is going to come out with this probability distribution. I'm using GPT, it's always the same. Floor is 7.64%, and then we've got bed, couch, ground, edge, bench, and so on. And what we can do is we can do the sampling now. We've got to decide which token we're going to use to stick on at the end to continue that sentence. Greedy sampling, we always choose the most probable. So I stick floor on there, and we feed that back into the model, and it's predicting comma, 26.14%. So we've got a comma there, and then we get and that's going to continue. So these sequences, like the cat sat on there, they're going to be variable length, because we can send in large inputs, sometimes up to tens of thousands of tokens we can send as our inputs in there. The sequence order is important, the order of these words, not just the words themselves. So this is a statement saying the film was not bad, in fact it was very good, versus the film was not good, in fact it was very bad. There's going to be the same tokens in here, however, there's a different order of those tokens. So the ordering is very important. That will help to determine the sentiment. We've also got long-term dependencies. If the cat sat on the floor and it had just been cleaned, then we're going to assume that it is referring to the floor. Versus it has just been fed, then it probably refers to the cat. And the attention mechanism is what is going to help the model to understand what it means by looking at how tokens are connected to other tokens. And we'll look at that a bit later on. And then we do our prompt engineering. We've got a prompt like this. You're a friendly and good-natured chatbot, we give it a persona, we give it some instructions. It's going to answer user questions without generating any inappropriate output or insulting people, and then we ask it the question. And we can do RAG, where we just stick additional information into the prompt, we retrieve the information, we augment the prompt, and we're going to generate the response to that particular question. Chat history is important. If we ask it, what is the capital city of the Netherlands, it's going to answer something like this. This is actually the output that came from GPT-2 when I was at the GoTo conference in Amsterdam. I said, is it nice there? Now, if we say, is it nice there, that doesn't make sense unless we've got the context of the user asking the question and the chatbot giving that answer. And the chatbot actually responded, I was doing it on the speech synthesizer. Yes, Amsterdam is a nice city. What can you do in Amsterdam? And the chatbot said, you can do lots of things in Amsterdam. It's only GP2, but it knows about Amsterdam. Yeah, so quick demo of that. I built a chatbot on GPT-2. So let's run it. Start this thing without debugging. And it's going to load up GPT-2. I'm only running on the CPU, but it's a very small model that works. Hi, I'm GPT-2, a friendly chatbot. I can help you. What is the capital city of Oslo?
I'm ChatGPT, a friendly chatbot. How can I help you?
Yeah. And it's you can see it's not giving such a great answer there. It's only GPT-2. So when this model came out, I got excited. Not many people got excited because it wasn't that great a model. But Sendex on his YouTube channel, he actually borrowed this kind of huge machine with a load of GPUs, and he downloaded loads and loads of Python code from GitHub, and he actually trained the GPT-2 model as a code generator. And this was revolutionary because we didn't have any co-pilots. And he was amazed. After the first day, after 24 hours, he's coming back and he's basically putting in code. Oh, wow, I can put in Python code. And it's actually generating additional code. And some of this code actually runs and compiles. It does make sense. And I kind of saw the potential of that, even though that hadn't really taken off. It wasn't until GPT-3 that more people started taking it seriously, and then the world took it seriously with GPT 3.5 Turbo, and everything sort of came to life there. So they're good at doing these. Oh yeah, the sequence prediction demo I'll run quickly. This is in the notebook, so you can actually run through these examples if you like. And I've got the GPT-2 implementation here. So we'll talk through the implementation later, but we just install a bunch of stuff. The model is based on PyTorch, which you may have worked with if you've been doing any kind of machine learning with vision models and starting to look at the language models. So it takes a few seconds to bring in all of those namespaces. The next thing we're going to do is we're going to go to Hugging Face. I'm going to generate the GPT-2 model, and I'm going to save the model weights down into gpt2.pth. So if I reveal in File Explorer, we've got the gpt2.pth, and you can see there that's about 480 meg of floating point numbers. That's all of those actual parameters. We can actually print the model. And here we can see we've got 12 layers, 0 to 11, of 12 attention heads. And that's just basically showing the actual model structure. At the end, we've got a linear layer. And we've got the token embeddings and the position embeddings. We'll talk about those later on. This is just doing a bit of parameter calculation. I don't know if I need to run all of these, but I'll do these anyway. And then we got onto the GP2 implementation. This is defining the model. It's saying the block size, the vote, that's how many tokens we can take in. Token vocabulary size is 50,257. 12 layers, 12 heads, and 768 dimensions in the embeddings. So that defines what our model is going to be. If I make those values bigger, we get a larger language model, like Phi 3.5, I think that uses 32 layers of 32 blocks and 1,500 dimensions. These are the various layers of the network. We've got the self-attention, we've got the multi-layer perceptron, and we can use that to define a block, and then we can actually define the model itself. So it's not that much code that we are using there. So again, this is the implementation using that code above to create the model. And then we can test the model. So what I'm doing here is I'm saying the cat sat on the. Stockholm is the capital city of. I'll actually put a Norwegian one in as well. And we can drop in Oslo there. So if I run that, what this is going to do is I'm using matplotlib to display the results. I'll just change that to 20, the font size there, and let's run that again. So all I'm doing is I'm giving a sequence of tokens to the model, and I'm looking at what comes out. So look at that on there. We've got space floor, space bed, space couch ground, those options there. Stockholm is the capital city of. It's predicting Sweden as being the most probable, or the Kingdom of Sweden. What's quite worrying is we've got Norway, Denmark appearing here. Oslo is the capital city of. It doesn't have a clue. Python developers, it understands languages. You typically import NumPy as NP. The king of rock and roll is Elvis Presley. Tokens aren't always words. This is space Pres, and then obviously it's going to be Lee after that. But it could be the king of rock and roll is Elvis, full stop. We don't need to mention his surname, he was that famous. Or the king of rock and roll is Elvis, comma, and he was famous for blah, blah, blah. Or Elvis Costello, 2.76% chance that could be true. Sometimes it's very evident what the next token is going to be. The king of rock and roll is Elvis Presley. It's almost certainly going to be Lee that follows there. If it's your favorite animal or your favorite pizza topping, then it's a lot less certain. Now, the model will always give out these results. It's the sampling process that is going to add the actual randomness or stochasticity to the model outputs. So we're feeding in a model. We've got this diagram that we saw in the previous session, which is the architecture for the transformers, and it's generating a response for us. However, neural networks don't really do text. They don't understand text. So we have the concept of text tokenization, of actually converting the input text into a series of integers that can be used. So this is what it used to say on the website. I really love this text because it mentions 3 things that are really, really important about tokens and about language models. Tokens are common sequences of characters found in text. Very often when we're showing examples of language models, we refer to the tokens as being words because that's easier to understand. But we've got text tokenization. And the reason that tokenization is split into 2 tokens is token is a word that's used very commonly. Ization is a suffix that we can use to turn that words into other words. So computerization, digitalization, hospitalization. We've got all of these different word combinations. So it goes through and you give it lots of text and it statistically calculates using, I think it's byte order encoding, the most optimal way to represent that text corpus in terms of 50,000 or 100,000 or 200,000 tokens, depending on the size of your vocabulary. Andrej Karpathy has another video, 2.25 hours, where you can build your own tokenizer, and he explains how these tokenizers work. The first 30 minutes is just the theory about tokenization, which is really, really interesting, and then he gets into writing the Python code if you do want to go through the rest of the module and code that up. So this is what this looks like, and we get a series of these integers. So that's going to be 45 tokens if we're using English. So the word the is represented differently. So the is not always the same token. Sometimes it does not have a space and it has a capital T, then it's 464. If it has a space before it and a capital T, it's 383. And if it has a space and it's a lowercase t, then it's 262. So they will all have a very similar sentiment, very similar meaning, but because the characters are different, they're represented using different tokens. If we do this in Swedish, 83 tokens. I'd imagine it's very, very similar if we did it in Norwegian. Oh yeah, we got the Norwegian one there. Yeah, 72 tokens. I've done this presentation in lots and lots of different countries. You can see there. And this is with the GPT 3.5 tokenizer that has, I think it's the R50K base, 50,000 tokens. We can see that those words are quite fragmented because there's less Swedish than there is, and Norwegian than there is English in the training data. So we haven't got the statistics to make that viable to use full words as tokens. Mechelanian, that's where the language that a few people speak in Mechelen in Belgium, 71 tokens. Dutch, 71 tokens. Finnish, 103 tokens. Telugu, 622 tokens. Now, the reason this is happening is because that when they trained or created that tokenizer, Telugu was not really used in the training data. You could argue that it's a minority language. 10 million people in the world speak Swedish, 100 million speak Telugu. Nowadays, things are different. It does understand more about Telugu. Telugu is spoken in India. It's one of the Indian dialects. So we say that English is the new programming language. We prefer to write the prompts in English. You can see here, using different languages, there's different efficiencies in the tokenization using those languages. With English, and this is comparing it to English, the amount of tokens per 1,000. So English is 1.0, Telugu is 8.8. And you can probably find your languages on there. Swedish and Norwegian are very close at 1.8. And then there's this MLU that Jody was discussing. If we go to a larger model, we have better understanding, and you can see that the language is dependent on the efficiency is dependent on the language in this particular test. And we've kind of got this correlation between accuracy and token efficiency as well. That looks something like that. So the reason I say English is a new programming language, and I recommend writing your prompts in English, is that GPT models are most accurate within English. Billing is based on the number of tokens. Throughput is based on tokens per second, and the models have a maximum number of input tokens. If you're a developer and you can make something more accurate, you can make it cheaper, and you can make it faster and able to process more information just by choosing the language that you're doing the prompting. It's a good choice to do that. I asked it, how do I make cheese in Telugu? I tried to do that, actually. I Google translated it, and I was giving this a course at a bank. One of the developers put his hand up, and he says, I run an Instagram group, and I manage the group. We've got 100,000 users in the group, and it's a group that talks about the Telugu language. That isn't how to make cheese. It's something very, very similar to how to make cheese, but I blame Google's translation for that. So I asked it, and this was back in the early days. It did its retrieval augmented generation. It generated an answer, and it came back with this. No idea what that meant, so I put it back into Google Translate, and it comes up with this. Cheese powder is the main ingredient in making cheese, apparently. Curd, pisa, dal, jiggly, geelcar, powder, and curd. So, yeah, it's not a great explanation. Then the model gave up. If you're interested in something more creative, I can generate a poem or a story for me. Let me know if you want me to do that. Also, here is the image of the Frozen movie characters, Anna, Elsa, Kristoff, Ostaf, and Sven, in an ancient autumn-bound forest of an enchanted land that you requested. I hope you like it. So something's wrong here. It's just not understanding what I'm sending in. Now, that's just a fun example that I put in. It is a lot better now. It will give a much better response. I've tested it with the better tokenizers and better models. But it's just showing how language will affect understanding. There is this, if you're in a Scandinavian country, there is a GPT SW3. I think it's based on GPT-3 or some other model that's been created by Sweden AI. And this has, it's been trained on Swedish and Norwegian and Danish and Icelandic and English and some programming code. I've never used it, but I was doing a presentation at Stockholm for the Stockholm AI group. And I says, has anybody used this model? And this guy put his hand up and I goes, what's it like? And he goes, it's crap. The more powerful language models are going to be better than this model there. So going up, this is just summarizing, going up to a better model gives you a better understanding. Also on the subject of tokens, Space Solid Gold Magikarp is a token. And this confused people when they were developing language models. So they went in to the model and says, what does the string solid gold Magikarp refer to? And the model responds, the word distribute refers to the act of distributing or spreading something amongst a group of people or things. So this was one of these glitch tokens that, for some reason, the model doesn't understand those. There is, believe it or not, a forum on Reddit, a subreddit called r/counting. And this is what they do. So it's a bit hard to read, but the start of this thread is 3,714,000, and then you've got to respond with the next number, 3,714,001, 2, 3, 4, and so on. So it took 4 counters, 1 hour, 5 minutes, and 39 seconds to do 1,000 of those numbers. Solid Gold Magikarp did 500 of them. So when they trained the tokenizer, they were using data from Reddit, and because of r/counting, solid gold Magikarp was so prolific in the training data that it made sense that solid gold Magikarp was a token. When they trained the language models, they revised the data and they thought, well, let's just get rid of r/counting. It's not that much use. We're not going to learn that much from it. And it wasn't included in the model training data. So although it's in the tokenization, it is a token, the model never know what solid gold Magikarp was. I don't know if you watched the film last night, but you know, if we've got the rise of the robots and we need to defeat the machines, it's not John Connor or Neo. It's going to be solid gold Magikarp that we've got to track down. Unfortunately, the user account has been deleted and they're not present anymore. So we can go through and we can iterate the tokens. I think I've got that in, I've got that in this demo here. I'll turn the volume up for this one. And let's run this. Did you hear that? That's the bell sound, because one of the characters when you print it into the console is the bell character, and that makes the bell sound there. So the first 256 tokens are just basically, you know, characters and UTF. A lot of those we can't display in the console, and this means because it can do UTF, anything can be encoded into tokens, even if it's not present as the actual, you know, tokens for that language. And with Telugu, all of the numbers, it was using UTF-8 encoding. That's why there was more tokens than there were characters, because it has to UTF-8, and that's a multi-byte encoding format. And then we get into all of these word fragments that we get here. So this is just basically what the tokenization vocabulary looks like for GPT-2. We can also go in, and there's this Jupyter Notebook on tokenization. So what I can do with this one is we're importing tick token, which is a Python library that we can use for tokenizations. I've got some sentences in here, the cat sat on the mat, and then token efficiency is dependent on the language of the text, and we've got that in different languages. So what I can do is tokenize that using the GPT tokenizer, and we see how many tokens we're getting, we see the token sequence. We can see in a bit more detail, oh yeah, that's doing the iteration of tokens. Here we can see in a bit more detail what the actual tokens are for those specific languages. Here I'm using Chinese and Telugu, and you can see that it's not able to display those actual characters. So there's different tokenizers that we can use for different models. So what I'm doing is I'm going through a few popular model names and I'm getting the tokenizers. So GPT uses GPT-2, ADA, and I think GPT-3 uses the R50K base. GPT-3.5, we've got this 100K base, and then we go up to the 200K base for the later models. The number there, like 50K, 100K, 200K, is in addition to the character encoding tokens, how many actual tokens are used for the words. The larger tokenizers are going to be more efficient. So we can run this. And we can see that thankfully with Telugu, that now goes to 22 tokens instead of 148 tokens when we use a tokenization vocabulary that has more tokens. So that's basically how the how tokenization works. However, neural networks don't do integers. They're not able to actually do integer processing. They all deal in floating point numbers. So what we've got to do is we've got to generate the embedding on the tokens, or the models have to, you know, during the training process, figure out what all of these different tokens mean and how they relate to other tokens. So if we take the token space cheese and we look at the embeddings for that, what we get in GPT-2 is 768 floating point numbers. So this is a vector in 768 dimensional space. Now, our brains can't understand 768 dimensional space, but we can understand 3-dimensional space, and you know, we're developers. If we built user interfaces, built websites, we understand about the red, green, blue color schemes. So the color Azure, 0127255. As data scientists, they would say, well, this is 0.51, using floating point numbers. And we can put all of the colors into 3D space, and we can understand that similar colors are going to be in you know, similar locations. We get this kind of pattern of colors. So when we're thinking about similarity, there's different ways of being able to calculate similarity between these high-dimensional vectors. One of the ways that we like to do this in most cases is something called cosine similarity. So if we're working with cosine similarity, what we're calculating is the cosine of the angles of the vectors. So the cosine of the difference in the angle between Azor and dark Azor is 0 degrees. The cosine of 0 degrees is 1.0. So as far as cosine similarity goes, these two colours are completely similar. And a graphic designer may say, well, this is just the same colour. You know, if you're varying the light in a room and it's white light, then the colours of an object is going to basically go along that line. So that's basically looking at the actual shade of the colour. Euclidean similarity is looking at the difference in the distance in that high-dimensional space. In this case, it's 3 dimensions. So you can use Pythagoras to calculate that distance there. And that would argue that cyan is more similar to Azor than dark Azor is to Azor. There's also dot product similarity as well. And I'll be talking this afternoon about vector search and vector search capabilities. So we'll go into more depth on how these mechanisms work. But typically, cosine similarity is what we use. Euclidean similarity can be useful for other scenarios. It's not always cosine similarity. So if you're looking at board games, a friend of mine at work said, you know, can you also use embedding to find similar board games? So here we've got the age and the game time of Carcassonne. And that angle is very similar as it is for Star Wars Rebellion. But that's for people who are 16, Carcassonne's for people who are around 8 or minimum age of 8, and the game time is about an hour as opposed to 30 minutes. Ticket to Ride there, the angle cosine similarity is less, but the Euclidean similarity is more. It takes a bit longer to play for minimum age of 9, I think, instead of 8. It takes about 40 minutes to play. So if your kids love Carcassonne, then you can probably introduce them to Ticket to Ride. So thinking about dimensionality reduction, there's a fantastic website called the Embeddings projector. It's created by Google as part of the TensorFlow project. And if I go to projector.tensorflow.org, what we've got by default is the Word2Vec 10K. I'll just drop this onto the dark theme because that's just cooler. So what this is doing is it's got 10,000 words. That's what the 10K stands for. And they're embedded with 200 dimensions. And right now we've done something called principal component analysis, which is basically taking those 200 dimensions and then putting them into 3 dimensions. So each one of these is a word. We can basically go around and we can see these words are highlighted. Now these, T-distributed stochastic neighbor embedding and unified manifold approximation and projection, these are what's known as unsupervised learning algorithms. And what they are going to do is find patterns in these embeddings vectors to be able to group similar items together. And when I run, the T-SNE is the best one because that actually animates whilst, it's not, I don't know if it's the best, it's the most visually appealing one, because once it's done with the nearest neighbours, what it's going to do is go through a number of iterations or epochs, and what it's trying to do is to cluster these words based on their embedding vectors and find similar words. So what we see, if we leave this running for a certain amount of time, is that clusters will start to form. It takes a few minutes. I've not got the fastest laptop. We'll just let it itself get organised until we do get some distinct clusters appearing. Let's have a look. Yes, I can probably pause it round about there. And you can see there's a big cluster over here. So we've got Rick, Barry, Jim, Dan. So these are all male names. If we go around here, we've got Cameroon, Liberia. These seem to be countries or cities in Africa. Down here, we've got American states. I'm not sure what those are. Oh, yeah. Yeah, it seems like religious things that we've got over here. And then here we've got musical stuff around here. So this is basically with words. We can do the same thing with tokens. We can also basically load a file here. And what I've got is, if I go to, I think it was this lab here, or was it this one here? No, I think it's in this lab here. If I open this revealing file explorer, what I've done is I've taken the tokens from GPT-2, or some of the tokens, and we've got this token embeddings.tsv, this TSV file. So what I can do is just copy this path, go back to Explorer, and we can load up our own embeddings. This is really cool if you're playing around with embeddings and you want to visualize them. So this is the TSV file for the tokens. And then we need the labels, which is going to be what the tokens mean. So I take tokens.txt, and I'm limiting it to tokens that are like 5 characters or something, and they are prefixed with a space. So it's showing these. This time I'm going to run the UMAP, which is a bit quicker than the tsne, but it does all of its epochs without showing the animations. So it's not as nice to look at, but that won't take too long. Be aware, there are a few root tokens, and they're all together in the same cluster. I say to my students, you can hunt for them if you must. I've never had them appear in a presentation. There's always a first time there, so apologies if anything inappropriate does appear on the screen. But if you go over here, you can see that we've got all of these, and these are relating to times, months, and weeks, and so on. Over here, we've got trophy, awards, medals, prizes, bounty. And here we've got shall, couldn't, can't, and so on. Over here, works, holds, helps, keeps. So these all seem to be kind of relating to similar words that mean something. So this is really how the language models will understand the actual tokens. We also have vector databases, which I'm going to be talking about this afternoon. These are really, really cool. I love them. You can find similar sentiment in text. You can find similar images. You can also use it in face detection, which is fun, but illegal according to the EU AI Act to do in public places. And you can do it for music, which is what I'm going to be talking about in the afternoon. We can find similar sounding songs. And this is what Spotify were doing in their music recommendations engine. So the transformer architecture basically looks like this. We're going to dive into a bit more depth and see how it works. It was covered in a white paper, which is called Attention is All You Need, because they were describing the attention mechanism. There's been different ways of building larger language models, and it's kind of evolved over time. And this attention mechanism, they discovered this is the main, the best way of being able to make predictions and to be able to build these language models. So that's why they've just said attention is all you need is the actual title. This was back in the good old days, before everything became popular, when researchers would make all of their findings and research available. So Google did all of this work. They published it as a white paper. OpenAI then took that work, did GPT-1, GPT-2, and then with GPT-3, they decided we're not going to share this information with everybody. We're going to keep it for ourselves. And now it's just become a lot more private with closed source models. There are some open source models available, but we do have that. And we went through a progression through RNNs, LTSMs, and transformers, and something else. We don't know what that something else is yet. I used to stop there in this slide, but I added that on because there will be something after transformers. We just don't know what it is yet. Quite frightening, really, because it'd be interesting to see how that actually develops and what does come next. So what we're really interested in is text prediction. The original model was about translating, I think, between English and German. So we had inputs in different languages, but now it's kind of this kind of like single block. So the output embedding is really the input embedding. And if you look at this bit, we're going to be sending in the outputs, and this is or the actual inputs to the model, and this is just going to be a series of integers that goes into the model. We're then going to do the embeddings of those tokens, the meaning of them, that's the token embedding, and then the positional of them, which is done in the positional embedding. So the text input comes in, the cat sat on the. I've chosen words because it's the, and then space cat, space sat on the. But they could be split, and it could be multiple tokens. If it was in Swedish or Norwegian, maybe it would have split the words. So we do the tokenization. That's fairly easy. The tokenizer does that for us, and that is something a process that's outside of the model. We then do the token embedding. So there's a lookup table in the model known as the token embeddings table. And in GPT-2, it is 768 by 50,256 floating point numbers. And each row in that table is going to be the token embeddings for the corresponding token ID. So this is just basically a lookup. We go to 464, 3797, 3323, 19, and 262. Do a lookup in that table, and that gives us our embedding vectors, which is going to be 5 by 768. So those slot in there. Now, as the the film was not good, in fact, it was very bad, versus the film was not bad, in fact, it was very good. The position of these tokens in the sequence is also important. So we also need to get the positional vectors. This is another lookup table, and GPT-2 you can send in up to 1,024 tokens. So the position embedding table is 1,024 by 768. And if we send the catsat on there, it just chooses 0, 1, 2, 3, and 4 from that, and that gives us the actual position embedding. One of the things about models is we can now send in a lot more tokens than we can with the older models. I remember working with GPT-3.5 Turbo. You could only send in, was it 4,096 tokens? And that was a problem. But nowadays you can send in hundreds and thousands of tokens in some of the large models. So the positional embedding is done differently in other models, because as that table gets really, really big, it's a lot of floating point numbers, and we do other methods. We use like sine waves, adding sine waves together to get the actual position and just generate them rather than having trained weights as they are in GPT-2. We add these guys together, and that's going to give us the encoder input values. And we can see how this works. If I go to NanoGPT, which is the implementation that Andrej Karpathy did. So if I go to this GPT-2 model raw, and we zoom out on it, that's GPT-2, 95 lines of Python, I think it is. I've ripped out all of the comments and basically optimized it a bit. So this is the version I actually use that has the comments in. So that's, 136 lines of Python, still not that much. And I've got some breakpoints in here on the actual inputs. So what I can do is I can go to the sequence generation, and if I run this with a debugger on, we should start to hit the breakpoints in the model. So what we're doing here is getting the actual token embedding for the input. That's in the actual constructor. What we're doing here is creating the token embeddings table, the position embeddings table, and the various layers within the network. If I continue here, we'll initialize the model, enter some text. If I press enter, it's going to take the catsat on there as the actual default input. And if we look at the code that I'm using, oh no, sorry, it's taken 99 bottles of beer on the wall. That's coming later. Let's just comment that one out. And send in the catsat on that. So again, I'll run it with a debugger. And F5 to the next breakpoint. So what we do before we actually call a model is we actually do the tokenizer. So I'm sending in the catsat on there, we get the tokens, we then actually generate these into a tensor. And we call the model by sending in the input, which is going to be the actual tokens. So within the actual model, if I go back to the GPT-2 model, if I go into the immediate window and drop IDX on here, that's the input to the model. Actually, I'll do IDX.toList. And you can see this is the tokens for the catsat on there. That we're sending in those IDs. So what we're going to do is to get the positional embeddings and the token embeddings for this. So if I just step over here, the first thing we do is we get the positional embeddings for that. So the actual pos vector here, if I look at pos.toList, that's 0, 1, 2, 3, 4. That's the actual positions. And the positional embeddings, if we look at this, just clear the window there. So positional embeddings is just a tensor, and the size of that tensor, or the shape, actually, if I can find it, it should be dot shape. That's 5 by 768. That's the actual position embeddings. And then what we do is we calculate the token embeddings. So if I step over the next line of code, press F10, then we should be able to see the token embeddings. You can see that's 1 by 5 by 768. So we're just using these tables to actually get the lookup. And then what we do is we calculate the input to the layers, which is adding the token embeddings to the position embeddings. So that's basically where we are in that actual stage of the network there. So what we were doing really is this. We're getting our tokens, getting the embeddings, getting the positional vectors, and adding those together, and that's going to be the input to the model. Now what happens next is this multi-head attention. This is the actual formula that takes place with the query, the key, and the value. So as Michelle was explaining in the previous session, we split the input into the keys, the query, and the values, and we get vectors like this. Depending on the number of heads in the model, I love the name of this. We've got this like split heads, which is going to split that output into 12 because we've got 12 heads. And that's going to give it now, instead of being 1 by 5 by 768, it's 1 by 5, 12 by 5 by 64. And each one of those are sent to the 12 heads, which will perform the formula that we saw a few slides back, which is this one here, on on those 12 times. And that's done in 12 layers. So that calculation is done 144 times. The attention formula is quite complex, but basically what we're doing is we're working with the key, the query, and the value to figure out how the words are relating to other words. So I've got an example. That's basically showing how the maths works for that. But the attention example I was using is the cat sat on the floor, it had just been cleaned versus it had just been fed. Now what I've done is I've embedded those with 2 dimensions, and they may fit into the 2-dimensional space, something like that. And you've got the distances between them. These are the similarities that we've got. Now if it had just been cleaned, then the attention mechanism will figure out that it has more attention, or it's closer related to the floor and closer related to being cleaned. So the values for all of those embedding information is modified as it goes through all of those layers. And that's what helps the model to understand the ambiguities that we've got within the languages that we use when we communicate with those. So to summarize, the model basically looks something like this, with all of the layers when we put that together, and there's 12 layers. And there's a linear layer at the end that's going to give out the logits, or the predictions of the probabilities of each token being the next token in the sequence. So what we can do now is we can actually generate text, if we can do that. So what I'm going to do is to go here, and we've got the sequence generation. I think it's this one here. Let's just run this. Running it without debugging, so it won't hit the breakpoints. So, oh yeah, I'll try this with a different one actually. The fun input to use for this one is the king of rock and roll is Elvis. So let's take that one on there, Control F5. So what we get here is I send in the king of rock and roll is Elvis, and here we've got the actual sampling process. So what we've got to do is we've got to decide out of these tokens. I'm showing the top 10 there. And it is deterministic. The models are deterministic. It's the sampling process that's stochastic. So we've got 64.98. If I run this again, we get exactly the same predictions. There. So what I can do is decide which of these tokens is going to go onto the end of the text to generate it. So first, I'm going to do greedy sampling. When I press enter, we're going to take the most probable token, we're going to put it on the end of there, we're going to send that into the sequence, it's going to come up with a prediction. So Lee is the next, the most probable there, so let's stick that on, and then we've got full stop. And then we've got space he, apostrophe s, a rock star, comma, and he's a rock star, full stop. He's a rock star. He's a rock star. It's only GPT-2, but if we wanted the models to be deterministic, this is what we'd have to do. We'd have to always take the most probable token, and they would always generate the same answer. However, they probably wouldn't be that useful because the answer would be it wouldn't be good, and it would be repeating itself a lot. The other models would do more sophisticated stuff there, but even I think when you're using a temperature of 0, there is some randomness in there. So if I run this again, I'm going to change the sampling process slightly, and I'm going to just introduce a bit of a randomness. My version of randomness is going to be me hitting return a few times and then pressing one of the number of keys. So Kong and Rock and Roll is let's just choose 2, and his band, comma, the Rolling Stones, full stop. Yeah. So it's getting there. And what I can do is just press enter a few times and just occasionally press one of these number keys. So what I'm doing is putting some kind of randomness into the actual process. So you can see here, I mean, it is generating text, and that text is more humanistic, even though it may not be factually correct. Remember, it is only GPT-2. And so, yeah, it is actually coming up with actual output text there. So that's what goes on within the sampling process, and that is principally influenced by a couple of parameters. One of them is the temperature. And basically, this is what the sampling temperature, this is a description that I copy-pasted from somewhere. It's between 0 and 2. Well, it's actually between 0 and there's no upper limit on temperature. But if you push the temperature too high, you can have a temperature of 100 or 1,000. It will start picking the characters very randomly, and it just starts generating text, and it just starts generating garbage and just weird characters. I think in the OpenAI portal, you can force it to do that. So this is why in the interfaces, in the model interfaces, you can't usually set that value above 1 or above 2. And lower values will make it more deterministic, but not completely deterministic. So what I can do is look at how the temperature works. And this is in the Jupyter notebooks that we've got. So there's a temperature theory. And what I can do is just run this. So I'm going to import some stuff. So we're creating a model in. I'm actually using a Hugging Faces model here. So we've got a prompt, once on a time in a faraway land, and we're just asking it to do completions on that. So I'm going to start with a temperature of 0.00001. Now the reason I'm starting with a very low temperature is there's a formula that's used to calculate temperatures. So this is the formula that's used in or can be commonly used. We take the scores, the outputs of the model, and we divide them by the temperature. So what happens if the temperature is 0? What's this going to do? So it is not this exact formula, but it's fairly similar to that. And what this is doing is it's going to adjust the probabilities that are going to be coming out from the model. So if I drop back here and run this cell, what it's going to do is generate 3 fairy tales where the temperature is 0. So you can see that these are completely the same. It's equivalent to 0, it's a very low number. And then as we start to increase the temperature, it gets more creative with these. It's actually putting in more random words. Now, dependent on our scenario, we're going to find a sweet spot where if we reduce the temperature, it's going to be less predictable. If we increase the temperature, it's going to be more predictable. So that's something that you can experiment with when generating the text. I'm not going to leave this thing running for too long. I have left it running at conferences, and I've been talking, and the whole audience falls about in hysterics, and I'm not reading it. I have no idea why. I have checked the recordings, and it has come out with something extremely inappropriate that's popped up on the screen for a few seconds as it's been running through that. Another parameter that we've got is top P, and this is known as nucleus sampling. And top P is a bit easier to understand than temperature. Temperature was this complex non-linear format, and if you know what softmax means and you play around with it, you'll see how it adjusts the actual bias. But top P is really easy to understand. And what this is doing, if I set the top P to 0.1, it can only select from the top 10% of that token distribution. So it can never choose couch or ground or edge. So the value of top P is going to affect how the tokens are selected in that way. So we can use a combination of temperature and top P to influence the outputs of the models. So what I did just for fun is to visualize this. If I go into demo videos, and we've got temperature top P. And what I've done here is using GPT-2, I've taken, I don't know why VLC is running slow on my laptop. It's painful. Yep. So if I just stop that and whiz back to the beginning, you can see here if you have 1.0, they have no effect on the probability distribution. With a top P of 1.0, we select from 100% of the distribution. With a temperature of 1.0, we're dividing the model outputs by 1, so we make no change in the model outputs. But as we start to reduce the temperature in the top P, the probability distributions of selecting tokens is going to change, and it's going to change in different ways. So you can see with top P, when we get round about to 0.5, all of the other tokens that are not shown are not going to be selectable. I missed it there. I was looking at the wrong graph, so let's just take that back. So you see the other tokens, and they've disappeared because that was a 50% certainty. And we can see here that the tokens are disappearing from the probability graph. In temperature, they're not. So the model could say the cat sat on the, and it could be something really, really inappropriate. That really inappropriate tokens are probably going to be very unlikely to select. So by setting top P to 0.9 or 0.95, we're just blocking out the 5 or 10% of tokens that are probably going to give inappropriate values. There is a bit more to the sampling process, kind of like a chess program, in that if you're only thinking one move ahead, if it's only thinking at one, that's just showing out these sections there. There's other options like presence penalty, frequency penalty. There's also the beam search. So if you think about a chess program, if you look at a chessboard and you only predict the next move and what the next move is going to be, your chess program is not going to be very good. But if you look several moves ahead and select the next combination of moves, then it's going to be better at playing chess. So a beam search does just that. It's able to go in and look at the top 3 tokens, and then from each one of those, it looks at the next 3 and looks at the next 3 and looks at the next 3. So instead of just basing it on the next token, it's basing it on the next sequence of tokens. I'm not sure how much beam search is used in the sampling process. I've not really had a chance to explore that, but there is a lot more complexity to the process than I've demoed in the actual demos themselves. I'd like to thank again the YouTube channels. Feel free to take a photo of this screen if you do want to check some of those. I'd most strongly recommend 3 Blue, 1 Brown and Andrei Karpathy there on understanding those items. If you would like the code for the Jupyter notebooks that I was running through, then that is available on that tiny URL there. It's the Jupyter notebooks that I used during my OpenAI workshop. And if you want to contact me onto the course, that QR code is my LinkedIn. Thanks very much for listening, and enjoy the rest of NDC.